Swayam Prabha. Digital India. Educated India.
So far in the class, you have looked at systems where there is a solid on a liquid or a solid on a fluid, some fluid, and it is either moving or the fluid is moving, and you found out the solution or the flow field in the liquid. Then you looked at another fluid on a fluid, right? Fluid and then a fluid, and then you saw translation of the fluid drop or the outer fluid, and then you found the flow field for both the fluids. Okay. So, in this class we will be considering a gas bubble on a quiescent liquid, gas bubble on a quiescent liquid. Okay, so for some motivation, I will talk about a system where there is a gas bubble and a quiescent liquid with some far field pressure oscillations. So, you know about moving machinery, right? Suppose you have a moving machinery like a pump and you have a trapped gas bubble on the pump. So, what happens is when the machinery moves, the far field pressure will oscillate with certain amplitude and frequency according to the motion of the pump. So, motivation. Gas bubbles on a pump, preferably a reciprocating pump. So, in such a case, suppose we have a small gas bubble, we will have a system where there is a bubble and far field the pressure is oscillating with some P sin omega t, suppose. This corresponds to the motion of the machinery that will give you that pressure oscillation. Okay. So, what drives the flow here is the pressure oscillation far away from the bubble. Okay. Lord Rayleigh in 1961, he was trying to derive this problem, and what he did is he found an equation that relates the radius variation with respect to time. Okay. So, he found the radius variation of the bubble with respect to time using first principles like Navier-Stokes and continuity equation. Okay. So, that is what we are going to do. Now, I will just is the problem statement clear? We have a bubble and there is a far field pressure that is oscillating. Okay. P0 plus Pa sin omega t we will call it. Here P0 is the equilibrium pressure far away. So, assume that there was no pressure oscillation. Okay. In such a case, the normal stress balance on the bubble will be given by, suppose pressure inside the bubble is Pb, okay, and pressure just outside is P0, that is the equilibrium pressure that I talked about. Okay. So, Pb will be given by P0 plus 2 gamma by 2 gamma by R0, where R0 is the initial radius of the bubble. Is this clear? It's simple Young's modulus equation. Okay. We did a normal stress balance at the initial condition where there is no oscillation or no pressure oscillation. Okay. So, assumptions in this simplification are: first one is that flow is one directional, flow is unidirectional, in r direction. Okay. So, there is only radial flow. Okay. It means that we have ur, which is a function of the radial component and time. Okay. There is no u theta, there is no u phi, equal to u phi is equal to 0. In spherical coordinates, we only have r variation with respect to time. Okay. That means only the radial component of velocity is present. Another assumption is that flow is the liquid is incompressible. Okay. Next assumption is gas is compressible. So, if ever you have any doubts, you should ask me. Okay. I have a gift for whoever asks questions if you like it. So, okay. So, these are the assumptions that we have. Now, we need to solve for the usual governing equation, that is continuity equation and Navier-Stokes equation. Okay. So, governing equations. First one is continuity, is del dot u equal to 0. Okay. In spherical coordinate, oh sorry, I will write Navier-Stokes also. Navier-Stokes is also there. So, we have rho dou u by dou t plus u dot del u into minus grad p plus mu del square u. So, these are the two governing equations that we will be solving. Boundary conditions are, so far what all you have, what boundary conditions have you learned for two phase systems? Suppose you have two phases like this, gas bubble, there is gas and liquid. At the interface, what all boundary conditions do you know? No slip. So, that no slip is called kinematic boundary condition. Okay. So, I will explain this kinematic boundary condition. So, no slip that you mentioned is actually continuity of velocity at the interface. No slip is applicable in the case of where there is a solid and a liquid, because solid does not move. Suppose there were two liquids, then the liquid at that tangential condition will be the same, or the flow close to the interface will be the same for both of them. Shear stress balance. Okay. Second is shear stress balance. Okay, there is one more stress balance. What is that? Normal stress balance. Okay, that also is a boundary condition. So, all these are applicable at the interface. Okay, at the interface. of the bubble. That is r equal to capital R as a function of time. So, the radius of the bubble is varying with respect to time, right. That is why I have written r equal to r of time. Okay. So, these are boundary conditions at the interface. What is the other boundary condition that we know? This one, far away the pressure is oscillating. Okay. So, that means P infinity or P infinity is written as P 0 plus P A sin omega t. So, if you look at this expression, it is like we are adding a certain oscillation. There is an equilibrium pressure that balances the bubble. You are adding a pressure which is oscillatory, P A sin omega t. Okay, this is as simple as that. So, what do you expect for this flow? As pressure increases, the far away the bubble will reduce in size. Okay. Then again eventually pressure will decrease, then bubble will increase in size. So, what we observe here is an oscillatory radial variation. Okay. So, what Rayleigh derived is a equation that governs this radius variation with respect to time. Okay. So, those governing equations we need to simplify. So, first we will take continuity equation. Continuity equation okay. So, no, go you are. So, this is your continuity equation in spherical coordinates. Okay. So, I mentioned before that UR is a function of R and time, U theta and U phi are absent. Okay. Both are absent. Okay. So, what we have here is these two terms will go away. So, we have 1 by r square dou by dou r of r square u r, where r is a function of r and t, is equal to 0. Is it clear so far? Continuity equation. Simple, I did not do anything, I just cancelled off two terms. Okay. So, you can remove this equal to 0. Now, what we will write is dou square u r, where r is a function of r and t, is some function of time h of t. Okay. I am following the notation from Rayleigh. So, Rayleigh advanced transport phenomena. Transport phenomena. Okay. Page number 250 onwards. Okay. Now, what we will get here is u r anywhere in the domain is h of t by r square. Okay. Some variation with respect to time divided by r square is the radial variation. Yes, yes. So, we will be solving for only the liquid side. Okay. Gas side is inviscid. We are not concerned with the velocity field in the gas. Okay. I will explain what is happening in the gas later. So, yeah. So, we will seek solution for this using kinematic boundary condition. So, h of t we will find using kinematic boundary condition. So, what is kinematic boundary condition? I will just write here. We found that u r is h of t by r square. Condition. This is nothing but, suppose we have a moving surface. Okay. The surface is governed by capital F equal to 0. Okay. So, here we had a derivative, right? So earlier you saw r square dou by dou r of r square ur equal to 0. This was the equation that we were solving, right? Now, if we remove this because it is equal to 0. Now, if you take integral of this partial differential equation, we will get a constant, right? So, that constant was h of t, ur r is equal to h of t. That is the constant we get from integration. Since it is a partial differential equation and ur is a function of time and r, we do not know that time variation, that we need to find out. Okay. So, to find this h of t only we are using kinematic boundary condition. So, suppose there is a moving fluid boundary that is given by capital F equal to 0. Okay. Then all particles close to the surface, they will effectively have no Lagrangian motion. So, what it means is capital df by dt is equal to 0. So, this is kinematic boundary condition at the boundary, that is at interface. So, here can anybody say the interface equation or capital F? So, the interface is given by small r equal to capital R of time, right? The interface or the bubble surface is given by capital R of time. Okay. We do not have any theta or phi variation. The bubble does not deform in theta, phi, etc. Okay. The bubble is stationary, bubble is always circle. It will have concentric motion if you look with respect to time. Okay. So, this is our equation. So, capital F or the equation of the interface is given by small r minus capital R of time. Okay. This is the capital F that will be substituting in the material derivative. Okay. So, we have r minus capital R and material derivative is given by dou by dou t plus u dot del of capital F equal to 0. Okay. Is it clear so far? Capital F is the equation of the interface. It is a mathematical jargon, as in how is the interface defined. So, here interface is given as radius equal to r of t, where r of t is changing with respect to time. Okay. So, this material derivative we need to find. We have dou by dou t plus u dot del f equal to 0. Okay. So, here what I will do is, I will divide the entire expression by magnitude of grad f. Okay. I do this so that this expression, okay, this corresponds to the normal to that interface. All these are mathematical jargons. If you it's not clear to you, you can refer to Gary. Okay. So, grad f by mod grad f, that is the normal to the interface that we have, where f is the equation of the interface. Okay. So, here we have 1 by grad f plus u dot n, where n is the normal to the surface. So, if this is the bubble, this is the normal to the bubble outwards. Okay. Now, to find this, we need to substitute this equation in f equal to r minus r of t. Please do it, you will get something. Okay. So, what is grad dou by dou r of r cap plus 1 by r dou by dou theta cap plus 1 by r sin theta dou by dou f phi. Okay, phi cap. Okay, this is the gradient in spherical coordinates. Okay. So, if you take grad of f, what do you get? F is given by this. Okay. you take grad of f, you get this theta and phi are not there in the expression. So, both theta and phi component goes away. You only have a radial component and the magnitude is 1. So, we have dou by dou r of r minus r of time. Okay. This derivative is 0. Capital R of t cannot be differentiated with small r. So, what we get is 1 r cap, that is the value of grad f. Okay. Grad f by mod grad f is r cap. So, this is the normal. So, what I have derived here is nothing but the radial component or the radial vector from the center of the bubble, that is giving the normal to that surface. It just means that bubble does not have any interfacial oscillation. Bubble is not deformed or anything. It is always a circle and it is inflating and deflating. That is why the normal to the surface is always the radial component. Is it clear? Now, if you substitute this in the normal stress balance, what you get is 1 by 1, okay. This magnitude is 1, dou by dou t of r minus capital R, okay, plus u r cap plus u theta, which is 0, okay, 0 theta cap plus 0 phi. You are dotting with this alone, okay, only r cap plus 0 theta cap. I am just writing this for understanding, okay, nothing. So, what you get is ur, that is all. You dot it with the normal, you will get only ur, both other terms are 0. So, what do we get? We have minus dr by dt. The partial term will become normal differentiation because r is only varying with respect to time, plus ur is equal to 0 at r equal to capital R. Okay, that was the kinematic condition. Okay, this is defined as equal to 0 at r equal to capital R. ur is given by dr by dt when r is equal to capital R. Now, suppose you substitute, so this is only valid at the interface. Okay. We will use this on that general equation that we found throughout the liquid domain to find h of t. Okay. dr by dt ur is at r equal to r is given by this, and ur everywhere in the domain is given by h of t by small r square, okay, which means that h of t by small r square at r equal to capital R is given by dr by dt. Okay. Now, we have h of t by capital R square is equal to dr by dt. We have h of t equal to r square dr by dt. I mean, I did not do anything big, it was only radial component of continuity that we solved and got an expression. Then we used the kinematic boundary condition to solve for the constant in that expression. Okay. So, now we have the value of ur. ur is given by r square dr by dt by small r square. Okay. That is, I just substituted h of t value here. Okay. Now, what does this mean? What does this mean for our flow field? ur or radial velocity velocity decays as 1 by r square far away from the bubble. Okay. One thing that we can infer from this equation, okay, dr or capital R, which is the radius of the bubble, it varies only with respect to time. So, if you look positionally, we have a bubble here. Suppose we consider a fluid element far away at point small r. Okay. So, what it means is that the fluid motion or the fluid element here will experience a greater velocity compared to the fluid element here. Okay. Farther we go away from the bubble, the smaller the radial velocity. So, the fluid flow here is just governed by one thing, that is oscillation. The fluid just oscillates radially. Okay. The magnitude positionally is determined by 1 by r square. Farther away from the bubble it decays, and magnitude of velocity is governed by radius variation of the bubble, which is capital R. Okay. It is also governed by velocity of the bubble, velocity of interface, which is r dot. R dot I will call as dr, dr by dt I will call as r dot. Okay, because it is only one derivative and just calling it as r dot. So, another thing is the magnitude will also vary positionally. What I mean is, suppose you look at one direction alone, then the magnitude will be governed only by the type. Okay. Now, so far we have used the continuity equation to solve for UR, which is the radial velocity variation. We found UR equal to r square r dot by small r square from continuity. Okay. Now, we seek to find radius variation, or we see capital R using Navier-Stokes equation. Okay. So, coming to Navier-Stokes, in radial Navier-Stokes in spherical coordinates is given by this. Dou r Okay. I have removed all the u theta u phi components in the radial Navier-Stokes equation. Okay. Theta and phi components of Navier-Stokes equation are trivial, they will just go away because theta and u theta u phi are 0 and there is no variation with respect to theta and phi. Okay. So, essentially this is your Navier-Stokes equation. Okay. So, what we will do is, we will substitute the UR expression in Navier-Stokes equation, okay, and then we will solve. So, first we will substitute in the, we will find and solve the right hand side first. Okay. So, right hand side we have minus 1 by rho dou p by dou r, okay, plus one big expression for the viscosity term or the viscous force, dou by dou r of r square of dou by dou r of r square r dot by small r square minus 2 r square r dot by r power 4. Okay. Please simplify this term, okay, and let me know what you get. So, did anybody finish solving? No. Okay. Okay. What did you get? Okay. It is 0, or the viscous stress as such is 0. So, what is the reason for it being 0? Viscous stress is 0 because why? So, assumptions that we made as fluid is incompressible, and second is that flow is unidirectional, right. So, that is the main reason why the viscous stress tensor becomes, viscous stress becomes 0. Okay. So, viscous stress is 0 because fluid or liquid is incompressible and flow is unidirectional. So, what is the characteristic of unidirectional flow, which means only radially it is flowing, or flow is irrotational. Okay. So, irrotational and incompressible flow will translate into the viscous tensor being, viscous stress being 0. Okay. So, what mathematically suppose you want to understand, there is an identity that says del square u is del dot u minus del cross u. Okay. This is an identity, mathematical identity for any vector. Del square u is del dot u minus del cross u. So, here del dot u is 0 because it is incompressible, liquid is incompressible. Next thing is flow is irrotational, that means no vorticity, or del cross u is 0. Both these terms are 0, so del square u is 0. Okay. If you are confused and you do not understand del cross u is 0, then you can do the exercise, that means so del cross u is given by one big expression. You can substitute and see sin theta, theta cap by r sin theta, phi cap by r, dou by dou r, dou by dou theta. This is a matrix that was discussed in earlier class. So u r u theta and r sin theta u phi. Okay, you can substitute this ur value alone. Ur value here is that expression r square r dot by small r square. U theta u phi both are 0. Okay, 0 0. So essentially you need to calculate only this matrix. What you will get is theta cap by r sin theta dou by dou phi of ur, okay, minus phi cap by r dou by dou theta of ur. Ur we know does not vary in theta or phi. Okay, so this expression as a whole is 0. So what we have done here is that we have proved that the flow is rotational. We already know from characteristic that flow is only in r direction, but we just wanted to solve and show that flow is rotational also. So rotational means del cross u is 0, incompressible means del dot u is 0, hence the viscous term is 0. Okay. So viscous term being 0 does not mean that the fluid or the liquid is inviscid. Okay. So mu del square u being 0 does not mean liquid is inviscid. Okay. Viscosity will return in our normal stress balance. Okay. Viscosity will appear in normal stress balance. Okay. Okay. So RHS of that expression is essentially just this term. Okay. The other term just goes away. Now coming to LHS. Please solve it. You can substitute ur value in the left hand side and find the expression or solve for the left hand side. So do not forget that r is a function of time. Okay, capital R is a function of time. Dou by dou r of r square r dot by small r square. Solve. This also will simplify into a good expression. So r dot square by small r square plus r square. So r double dot that I am writing here is just d square r by dt square. R dot is dr by dt. Okay, and r double dot is d square r by dt square. Just for ease of writing, I am writing as r double dot by small r square plus Did everybody get this? Okay. This is equal to minus 1, oh sorry, minus 1 by nu, right? Oh, sorry, 1 by rho dou p by dou r. Okay. This is our Navier-Stokes equation after substituting the UR value. Okay. So, we can see here that the radius variation is still not apparent because we have this small r in the equation. Okay. So, to eliminate small r, what we will do is we will integrate this governing equation over the entire liquid domain. Okay. So, what we get here is we will integrate this equation over the entire liquid domain. So, integrating over entire liquid domain. So, what is the range of the liquid domain? Please respond. So, we have liquid from infinity. Okay. So, what is the it goes from r equal to r to infinity. Okay. R to infinity we have to integrate. Okay. So, r of t to infinity. Here also from r of t to infinity. Dr and dr. Okay. Please do this fast and then we will conclude the class what we get. Okay, from r equal to capital R to r equal to infinity or r tends to infinity. This will give us minus 1 by rho pressure in the liquid side at r tends to infinity minus pressure in the liquid side at r equal to capital R. Okay. Oh, sorry, minus is not apparent. Okay, all we did is we simplified Navier-Stokes by substituting UR equal to R square R dot by R square, and then we simplified it by again integrating over the entire liquid domain. We did that to remove the R dependency as such. We need to find the radius variation as a function of time, that is why we integrated over the liquid domain. So, you simplify this, you should get something like R double dot plus 3 by 2 R dot square is equal to P liquid at R equal to capital R minus P liquid at R tend to infinity by rho. Okay. Were you able to obtain this? So, thing is that you substitute infinity, the entire expression goes to 0. Okay. You have minus of this by capital R power 4. You cut off everything, you should get something like this. Please check. Okay. So, according to literature, here ends Lord Rayleigh's contribution We will be looking at Plesset's contribution in next class. So, we do not know two expressions. So, we do not know the liquid pressure at R equal to capital R. Okay. In next class, we will find out this liquid pressure at R equal to capital R using normal stress balance, and then other pressures or pressures involved inside the bubble, how we will relate the pressure inside the bubble to the liquid pressure close to the radius or close to the interface, and so on. Okay.